In 1987, a worker in the village of Burake Bugo in Mali leaned over a water well to light his cigarette. Instantly, an invisible heat wave erupted from the dirt, followed by a continuous, shimmering blue flame. It took decades for scientists to properly analyze the gas fueling that fire. When they finally did, they found the well was emitting nearly 98% pure, naturally occurring hydrogen. Today, geologists call this white hydrogen. By mass, hydrogen holds nearly 3 times the energy of natural gas. When burned in a fuel cell, the only byproduct it releases into the air is pure water vapor. The flame in Mali didn't burn out after a few days. That accidental well strike tapped into a massive, self-replenishing energy source deep underground, offering a sharp contrast to our heavy reliance on manufactured fuels. The physical problem with hydrogen is that it is incredibly sociable. On Earth, it rarely exists on its own, instead binding tightly to other elements like oxygen or carbon. To use it as a fuel, we usually have to spend a massive amount of energy to force those elements apart. Most of what we use today is called gray hydrogen. Producers strip the hydrogen from methane gas or coal, a process that releases huge amounts of carbon dioxide straight into the atmosphere. This document shows the definitions for the different colors of manufactured hydrogen, including gray, green, and blue. Green hydrogen attempts to solve the emissions problem through electrolysis, a process that uses electricity from renewable sources to split water into hydrogen and oxygen. But that process requires enormous amounts of fresh water and electricity, making it highly expensive to produce. We are currently stuck in an industrial bottleneck. Manufactured hydrogen forces us to choose between a process that produces heavy carbon emissions and one that is simply too expensive to scale globally. The well in Mali ignores that bottleneck completely. Since the discovery, engineers have continuously extracted gas from the reservoir, yet the underground pressure hasn't dropped. The Earth is actively replacing the hydrogen as fast as it is drawn out. This image shows serpentinized mantle peridotite. The dark veins are sites of serpentinization, where underground water reacts with iron-rich ultramafic rocks. As iron oxidizes, it spits out pure hydrogen. Alongside it, radiolysis occurs. Natural radiation from uranium splits groundwater into oxygen and hydrogen. Because of these ongoing reactions, the Earth's crust acts as a continuous, passive chemical refinery. It generates a high-energy fuel without requiring a single watt of human-generated electricity. The scale of this natural production is vast. The U.S. Geological Survey estimates there are 5 trillion tons of natural hydrogen trapped underground globally. Extracting even a small fraction of that could meet global energy demands for hundreds of years. This chart illustrates the stark difference in production costs. While green hydrogen can cost around €5 per kilogram to produce, white hydrogen could be extracted from the ground for as little as 50 cents per kilogram. That severe cost advantage has triggered a global scramble. Exploration agencies and startups have aggressively filed for drilling permits across France and Spain, the United States, and throughout Australia. To understand how these new energy markets are evolving, hit the subscribe button below. Extracting white hydrogen presents a realistic path to resetting the overall cost of global energy. There is, however, a physical catch. Hydrogen is the smallest molecule in the universe. That makes it incredibly difficult to capture and keep in one place. Hydrogen molecules are so tiny they slip right through the wide atomic gaps of a standard steel pipeline wall. The gas causes embrittlement, a structural reaction where the metal loses flexibility and cracks, destroying pipes currently used for natural gas distribution. Even if we build better pipes, we face a biological threat underground. The subsurface is filled with microbial sinks, deep earth bacteria that absorb trapped hydrogen gas bubbles almost as quickly as the Earth generates them. The extraction industry faces a harsh reality. To build a viable market, engineers must locate highly specific geological traps and harvest the gas before the planet's own ecosystem eats it. There is also an environmental risk known as the leakage paradox. If white hydrogen leaks into the atmosphere, the gas chemically reacts with the specific molecules that normally break down greenhouse gases. Ironically, leaking this clean fuel could accelerate global warming. Extracting this resource safely will require highly specialized, leak-proof infrastructure. It also demands entirely new legal frameworks, as current regulations rarely account for drilling a gas that is neither a fossil fuel nor a mineral. White hydrogen offers a massive, naturally occurring energy reserve, but it requires highly advanced human engineering to properly contain and transport. The question remains, is the universe's smallest molecule the definitive answer to our energy needs, or will it slip through our fingers? Let us know in the comments if you think we can successfully tap into Earth's battery.